All right, thank you, Emily, for the introduction, and also thanks to the organizers for the invitation to speak. I'll be talking about some joint work with Fernando Badi and Shirley Gethin about, well, partial actions. So these are, well, different kind of object in a different kind of way in which groups can act on operator algebras. So let me start by motivating the very notion of a partial action. And I will do this through something that I hope is familiar to most of you. Namely, when we have an automorphism alpha of a C-star algebra A, then there is a 6-term exact sequence that helps us compute the K-theory of the cross product. This is the Tensor-Categories 6-term exact sequence that is, well, looks like that. And this is a very useful tool, even though it doesn't always completely determine the groups. But for example, in the case of the irrational rotational algebras, the K-theory of them is most easily computed using this 6-term exact sequence. And to apply it, of course, you need to have a C-star algebra that is a cross product by the integers. And how do you know if a C-star algebra is a Z cross product? Well, sometimes this is given to you by construction. In the case of the A thetas, this is essentially there immediately. But if you don't know beforehand that your algebra is a Z cross product, there is an abstract criterion that you can apply to check whether this is the case. And this is a relatively old result of Landstadt, which says that a unital C-star algebra is a cross product by the integers if and only if it has a circle action, which is supposed to be the dual action of the automorphism in question, and a unitary satisfying this condition with respect to the circle action. So gamma z of u is supposed to be equal to z times u for all circle elements. I will call this, in the next slide, an equivariant unitary. So equivariant unitary just means, for the next couple of minutes, this identity. And if this is the case, the way that you recover A as a cross product is by the fixed point algebra of the T action. Well, and the action is conjugation by this unitary, which preserves the fixed point algebra. Okay, so the combination of these two results, Tensor-Categories 6-term exact sequence for Z cross products and an abstract characterization of Z cross products is a powerful combination. However, as most of you may know, there's most of the most interesting circle actions are not dual actions themselves. So for example, this is typically the case for gauge actions on Kunz or Kunz-Pfister algebras. There are canonical actions of the circle on any A of algebra, on the turbulent algebra, and so on. These are very natural, very useful circle actions that don't have equivariant unitaries. So they are not dual actions themselves. And already in the 90s, Rexel in his PhD thesis showed that under mild assumptions on the action, much weaker than having an equivariant unitary, your algebra is isomorphic to a cross product by the integers, but not by an action, not by an automorphism, but by a partial automorphism. And in this context, a partial automorphism is just an isomorphism between two ideals of your algebra. This in particular applies to the algebras mentioned above here in this slide. So AF algebras are cross products by partial automorphisms, the same for the Kunz algebras and so on. And this is complemented by a generalization of the Tensor-Categories sequence for partial cross products by the integers, which looks like this. I mean, regardless of exactly what it says, the combination of these two things allows you to compute or recompute the K-theory of many interesting C-star algebras. And this is how partial actions came to exist. First for the integers, in order to be able to write some interesting C-star algebras as cross products by the integers by partial automorphisms.
Can I ask a question about that previous slide?
Sure.
You say that in the middle paragraph, A is isomorphic to the cross product of a partial isomorphism.
Yes.
What is the cross product? Is it A with the integers?
So the acting group is the integers, you're right. So A is isomorphic to B cross Z, where B is some other C-star algebra.
Okay.
And Z acts partially on B.
And B
perhaps
built somehow from I and J?
It is, B is the fixed point algebra of the circle action that you're assuming to exist.
Okay.
Perhaps it's a little misleading to say, to have written here A, so isomorphic ideals I and J of A. I should have written of B because it's really a different algebra where alpha acts. But in spirit, it's very similar to what I mentioned before about Landstadt's abstract criterion.
Thank you.
Yeah, thanks. And it did not take very long until the notion of a partial action was extended from the integers to arbitrary discrete groups. And the definition that I'm presenting here is to Excel and McClanahan. So we start with for simplicity, discrete group G and a C-star algebra A. And a partial action of G on A is a collection of ideals of A sub G, one for each group element, together with isomorphisms, alpha G, between the corresponding ones. So the domain of alpha G is AG inverse. The range of alpha G is AG. And we demand that the unit of the group has domain equal to all of A. So A sub 1 is equal to all of A, and alpha 1 is the identity on A. And also that alpha GH extends the composition alpha G and alpha H wherever the composition is well defined. So it could be that the range of alpha H does not intersect the domain of alpha G, and then the composition is not defined anywhere. And then this condition becomes empty. But whenever the composition is well defined, we demand that it agree with alpha GH. All right. Of course, perhaps all of you notice right away that there are not many partial actions on simple C-star algebras, because of course these ideals then will all have to be trivial for all of the algebra. And this is okay. The real purpose, or perhaps the original motivation of partial actions was not to study partial actions on interesting C-star algebras perhaps, but more to construct C-star algebras as cross products by partial actions. So perhaps realizing a C-star algebra that you're very familiar with, that you would like to study, and you would like to realize it as a partial cross product, perhaps by a commutative C-star algebra. And this can be seen in two ways. Taking cross products by partial actions, they will give you new examples of C-star algebras, but they can also give you a different way of looking at a C-star algebra that you already know. And this, of course, gives you more tools to study it. As basic examples of partial actions, of course, we have the global actions. These are the actions where all the domains are equal to the algebra itself. We have the trivial partial action, which is the one that has domains equal to 0 for all group elements that are not identity. And this is not the same as the trivial action, because the trivial action is, of course, global. This is a trivial partial action. All the domains are trivial except for the identity, which, of course, has to be all of A. And, well, a family of examples that come from dynamical systems was given through solutions to differential equations. They give you partial actions of the reals. So if you have an element of the real line, let's say T, the domain of this group element would be the set of all points in your manifold, let's say, such that the solution to the differential equation that you have with initial condition given by that point is defined at time T. Right. So another family of examples, and this is perhaps one of the most important ones, is are those given by restriction to an ideal of a global action. So it starts like this. We start with a global or genuine action. These are actions in the sense that we're used to, acting on a C-star algebra B, and we have an ideal A in B that we don't assume to be invariant. And then we can restrict beta to A. Of course, we don't get an honest action, because the ideal A is not invariant, but we get a partial action. the domains are defined in this way, and the automorphisms are defined in this way. So it's really at the level of the automorphisms, it's really restriction, and the domains are defined so that the restriction maps onto into A rather. And partial actions that arise in this way are called globalizable because they come from global actions. Not every partial action has this form. Not every partial action has a globalization. That is, it is known, there are intrinsic characterizations of when this is the case. And there are many tools to study partial actions. There is a notion or a version of the chi duality, many connections to groupoids, semi-groups, verbundles, notions of amenability, Morita equivalence, Morita globalizations, and so on. But, and here the bad news, things don't just work out the same way as they do for global actions. So this is in some sense how one feels when one starts learning about Hilbert modules. On the surface and at the beginning, it feels like everything is just the same, like a Hilbert space. And then one discovers, orthogonal complements don't exist. Direct sum decompositions don't exist, and things get very tricky. Some things just do not work the same way they do for Hilbert spaces, and this is exactly the same. Partial actions are much more delicate to work with, and as I mentioned, some things simply just fail in the partial setting. And I want to concentrate on finite groups to show some of the things that go wrong in the global setting. That is, for honest actions of finite groups, averaging arguments are used all the time. And for example, what they give you is that there is a conditional expectation onto the fixed point algebra, specifically given by this formula. And in the partial setting, this does not work because already in the very definition, alpha g of A, you're not allowed to apply alpha g to every element of your algebra, only to the ones that are in the domain of alpha g. The first actual difficulty is to realize what the right notion of fixed point algebra is. So what are elements that are fixed by all automorphisms? And then there you already start seeing that there are difficulties in even coming up with basic definitions. The correct version of the fixed point algebra is given by this. Notice that if xg inverse belongs to the appropriate domain, then its product with any other element of the algebra also belongs to that domain because the domains are supposed to be ideals. So the left-hand side here makes sense. Even though I cannot compute alpha g of A, I can compute alpha g of A times any element of the domain. And for A to be in the fixed point algebra, we demand that this identity hold for all elements of the domains. But these fixed point algebras are often too small, and there's in general no conditional expectation, faithful or otherwise, in fact, from A to the fixed point algebra. Another thing that goes wrong is that this very useful corner embedding that one has from the fixed point algebra into the cross product does not always exist. Right, so this is a problem. I mean, finite group partial actions just don't work the same way as global actions do. And in fact, and this is, well, going to the motivation of the project, what we wanted to do at the beginning is to study the cross product of partial actions of finite groups and also fixed point algebras, but mostly cross products, and getting motivation from the global setting. I mean, there's a lot of things that you can do if you assume that the action has, for example, the Rocklin property, in the sense of Gabor's talk last week, for example. So we wanted to, for example, define the Rocklin property in the setting of partial actions and then prove preservation results for the cross products. The first problem was really to get the right definition of the Rocklin property. I will not go into this talk. It was not easy. But then even once we had the right definition, the biggest problem was that, as Gabor explained last week, the Rocklin property is in essence, by the very nature of it, an averaging property. Yeah, you average with the projections that come from the Rocklin property and so on, but you average. And as I hope I try to show you in the previous slide, averaging just does not work in the partial setting. So these arguments break down in the partial setting. So what we had to do is really just take a step back and first try to understand partial actions of finite groups by themselves a lot better, so that we can hopefully later come back to, assuming the Rocklin property and prove more things. So the rest of this talk, what I will try to show you is the advances we made in understanding partial actions of finite groups. So I will not assume any type of Rocklin property. And the key notion that will help us understand the structure, the vague structure of partial actions of finite groups is the decomposition property. And I want to start motivating this with an example. Suppose your group is Z mod 3, and you act on a compact Hausdorff space X. This is really given by the choice of, okay, you have to have one domain for each group element. The domain of the identity element is all of the space, so you have only two further open sets, and you have a homomorphism from one to the other, and then you have the inverse, and that is your dynamical system. So the essential data is what is on this picture, right? So U1 and U2, they have some intersection. This is the U, and the symmetric. So in the V1 is the remainder of U1 when you take out U, and V2 the same. I'm just labeling sets in this picture. So this is a partial action of Z mod 3 on a compact Hausdorff space X. Notice that the restriction of our partial dynamical system to this intersection U is global, because U is preserved by, sigma 2, by sigma 1, and so on. So when you restricted your dynamical system to U, you get a global action, and those we understand very well. On the other hand, the restriction of the dynamical system to Y is take away from X all the domains. There's nothing happening. This is a trivial partial action, right? And this we also understand very well. What remains is V1 disjoint union V2, and how the dynamical system acts here is, well, V1 will be sent to V2, so that looks like a translation kind of thing, and there is some internal symmetry. Okay, so again, in this picture, the restriction to U is global, the restriction to the complement of everything is trivial, and then we're left with V1 disjoint union V2. Here, there's an exchange. You exchange V1 and V2, and you apply an internal symmetry. So we get equivariant extensions. So you decompose C of X with the ideal C0 of U into the quotient, and then you do it once more like this. Again, C0 of U we understand. C of Y we understand dynamically. And this one, V1 disjoint union V2, looks like we could have a nice description of it, this translation internal symmetry. And then it seems like the difficulty in understanding the system as a whole is really in the gluings, right? So how these sets are glued together inside of X, or in other words, the difficulty or the complexity is really in the extension or the two extensions. So this is pretty much just repeating what I said. And the entire complexity of the system is then encoded in how, well, in the dynamics of V1 disjoint union V2, together with the different gluings. Okay, we can do this for more general groups with more than 3 elements, but then the combinatorics get very, very messy and complicated. For example, one gets cardinality of G minus 1 extensions. In each of these extensions, the ideal looks like this action in V1 disjoint union V2, some translation and internal symmetry. And what we did is we isolated a property that these systems that we always get as ideals. We isolated a property that those systems have and studied it independently, because the goal of this was, well, the following thought: if we're able to understand all of the ideals that we get here of this form, here there's only one because the group is too small, but in general there will be a lot of them. If we're able to understand all of these ideals, then we can work our way up and recursively conclude that we understand our dynamical system C of X. So we isolated those systems. This isolated a property that they satisfy. We call it the decomposition property, and we study them independently. So to define this property, have to introduce a little bit of notation. So giving an integer, a positive integer n, tau n of G, so this is the n tuples in G. This is all subsets of G of cardinality n that contain the unit. Okay. And given one such tuple, we define A sub tau to be the intersection of all the AGs for G in tau. Okay, so this is again an ideal in A. And now comes the definition of the decomposition property. We say that alpha has the n decomposition property if A is in some sense canonically isomorphic to the direct sum of those ideals, right? So what I'm saying is, for each tau, one gets an ideal. Take the sum of all of them over this set tau n of G, and the composition property asks that A be isomorphic to that direct sum via specific map. The map is just taking all the elements in the coordinates and taking the sum of them. And therefore, the isomorphism is equivariant and so on. And we say that the action is just decomposable if it has the n decomposition property for some n. Okay. In particular, we're saying that these ideals, A tau, for different taus, that they are orthogonal inside of A. Again, alpha is n decomposable if A is isomorphic via the sum map to this direct sum. And the importance, and I was trying to hint at this a couple of minutes ago, is that any partial action of a finite group can be written as an iterated extension of the composable ones. Concretely, what I mean is that if G is finite and alpha is a partial action of G on C-star algebra A, then you can find, or they are canonical equivariant extensions like this, where the top one for the, so the extensions are between, well, 2 and canality of G. So at the very top in the middle, you have the system that you're interested in. And then all of the ideals have the K decomposition property. So at each level, you have the composition property of one level, of 1 degree lower. And the last quotient, which is this one at the very end, has the 1 decomposition property. And for those of you who are familiar with recursively homogeneous C-star algebras, this is reminiscent of that, how you decompose an AH algebra as recursively in a homogeneous way. Via these iterated extensions, you are in some sense lowering the complexity of your dynamical system. And in order to understand the complexity of alpha, it suffices to understand all of the systems that you get as ideals together with all the extension problems. Okay, so this is a tuple with, we described the internal structure of these decomposable systems to the extent that we can say that we understand them just as good as we understand global actions. And as evidence of that, for example, I want to show you this theorem. If your partial action has a decomposition property, so if it is decomposable, then it is globalizable. There is a canonical expectation onto the fixed point algebra, and also a canonical corner embedding of the fixed point algebra in the cross product. So these are the two things that I told you fail in general for partial actions. Well, for the composable ones, they are true. Also, being globalizable fails in general for partial actions of finite groups, but for the composable actions, it is true. And we can explicitly compute the cross product and the fixed point algebra in terms of, well, and these are global cross products in the fixed point algebra of a global action. It doesn't really matter the details, what is H tau, what is A tau. It does, what I want you to get from this is one can compute the cross products of these partial actions in terms of global cross products. And for these the composable actions, the things that you're used to doing for global actions, they work. So again, any partial action, you can decompose it recursively as iterator extensions of decomposable partial actions. And all of these decomposable partial actions, they behave like global actions. This is very nice. We understand the decomposable actions by the previous theorem, for example. And this means that the complexity of a general action alpha really lies in how these gluings are happening, how the different decomposable actions are glued together. And then, for example, so there are some properties that regardless of how complicated the gluings are, they will pass to extensions. Yeah? So the following properties we showed that are preserved by arbitrary partial actions of finite groups on C-star algebras. So nuclear exactness, finiteness of the civil rank real rank, and being of type 1. And in all of them, you can prove them all at the same time. For example, with the following argument, you first show it if alpha is decomposable. Okay, and if alpha is decomposable, then the motto is decomposable partial actions behave like global actions, and cross products, we can compute them in terms of global cross products. Morally, at least it should be true. And then in general, what one does is one decomposes the arbitrary partial action alpha recursively as iterator extensions of actions with the decomposition property. And then at each level, you work your way up. At each level, you know that, for example, being nuclear passes to extensions. And since the quotient and the ideal are nuclear because of the previous case of the decomposition property, you deduce it for the middle one, and then you go to the next level. Now, what used to be in the middle is a quotient that is nuclear. The ideal is also nuclear by the inductive assumption. So then, again, the middle is nuclear, and you work your way up to the cross product of A by alpha. Okay, so this is all I wanted to say. Thank you for your attention.